Okay, lesson 30. We're starting with geometry. Now, geometry, like you know it from grade 11, is still there. You're still going to be working with it. In the beginning, when I start showing you the first theorem of grade 12 now, you're going to see it's got nothing to do with grade 11, but it can. It will get to a stage where they're mixed up. So in the same question, you can have new grade 12 geometry as well as old grade 11. So you need to know those theorems. Now, let's press very far ahead or very deep into your brain, your craniums, and see, do you still remember the theorems? What are the theorems for grade 11?
Theorem 1.
Theorem 1. Fantastic. Right? Theorem 1 says what?
And the line from the center of the circle perpendicular to the chord.
Okay. And there's two of them. And you must have the correct wording for the correct one. So theorem 1 says the line from the center of the circle perpendicular to a chord will bisect. That's what we do in colored. So a line from the center of a circle perpendicular to a chord. What is the converse of that? When I give it to you as bisected and you deduct, it must be 90 degrees. So then we say line from the center of a circle to the center of a chord or to the midpoint of a chord or bisecting a chord, anything like that, but it must have the correct wording. You can't say that for here because it's not given perpendicular, you're deducting it's perpendicular. That's theorem 1. Let's get into theorem 2. What was theorem 2?
It's the one where the center of the
Angle is twice the angle of the circumference, right? So if this was 2a, then that would be 1a. That is the nice and easy, kind of like symmetrical one that you cannot ever miss if you see it. So that's the angle at the center of a circle is twice the angle at the circumference. And you've got to get the abbreviations correct. But there were a few things happening here, right, that you had to have a look out for. Namely, if it's squashed to the side, whichever side, because then it kind of like looks like the fourth theorem, the bow tie. But it's not, because that is not concyclic. So then that still will be 2a and a. What other ones are there?
When it's inverted.
Even this one, yes. When that angle at the center is twice the angle at the circumference, when it's squashed out. There's another one that you've got to keep a lookout for, when it's exactly on top of each other. That's still going to be 2a and a, because those are things that you miss if you don't look for it. It's in a sum and then you don't see it because you're not looking for it. Theorem 2, angle at the center is twice the angle at the circumference. You've got 9 coming. So theorem number 3 is
the semicircle.
angle in a semicircle is 90 degrees. So you've got to have a diameter. So the moment that the sum says AB is a diameter, then you've got possibly, you've got the angle in the semicircle. What's your abbreviation? Okay, please remember with all of them, you can still be asked, complete the following statement. If an angle at the circumference is subtended by a diameter, it will be 90 degrees. It's that one. Just the wording is a little bit different. If an angle at the circumference is subtended by a diameter, it will be 90 degrees. Happy on that? Okay. Actual fact, they sometimes consider this one still to be angle at the center twice the angle at the circumference. Because the angle at the center is 180. Twice the angle at the circumference, 90. Are you with me? Number 4, bow tie. And remember, often it's not a nice bow tie that you would go to dinner with. It's squashed in a corner or somewhere, and you've got to look for it. that those 4 points must be concyclic. Alright, so if that's concyclic, then that means that little angles at this circumference are going to be equal to each other. What do we say? What is the abbreviation?
Angles in the same circle segment.
Angles at this circumference subtended by the same chord. Is that the only way of writing it? What's the other way of writing it? Angles in the same
Circle segment.
diagonal. Angles in the same circle. What does that mean? If an angle is in a circle segment,
They're in the same side.
it means from there, if it's this angle, that segment. So this is not part of the segment. So if there's another one that's not in there but going over there, it's in the same circle segment. Alright, now thinking about that, there's also one that you must be on the lookout for here. That could be a little bit different. And that means if it's pulled apart in any which way, like that, maybe nice and easy to spot like this, or maybe it's more overcrossed over each other, where those two chords are exactly the same length, because now they're not in the same circle segment. They are angles
In equal.
in equal, and you can say segments, circle segments. Right. Number 4. Number 5 and 6 is your cyclic quad. Number 5
And
says
6.
what?
Okay.
This is 8 and this is?
18 minus 8.
Because the angles opposite each other are
Supplementary.
supplementary. So what do we say?
Angles.
Opposite
Sub.
are supplementary to each other. Is there any strange thing that I can think about there? Okay. Number 6 is the exterior angle. Now where's the exterior angle?
Outside.
Anywhere outside, as long as it's one of the sides that is extended. Can't do this and say that is an exterior angle. It has to be one of the sides extended. Then this angle will be equal to, and they go hand in hand. Very often people use the one rather than the other one. Because if I know that that is A, I know that this is 180 minus A, and still the opposite angles are supplementary. Or this one then is exterior angle of a cyclic quad. Now, thinking about that, let's do it last. Let's go to number 7, 8, and 9. What are my 7, 8, and 9 theorems? All about the tangents. So if you're looking at a sum and it doesn't have a tangent in, you're not looking for theorem number 7, 8, and 9. So number 7 says there's a tangent, and you're looking at the radius. And if it's a radius and a tangent in the point of touch, that must be 90 degrees. The moment that you've got 90 degrees somewhere, like in the semicircle even, the moment that there's 90 degrees, there's a possibility for Pythagoras. Even in theorem number 1, line from the center perpendicular, could be a possibility for Pythagoras. Okay, so this one says radius perpendicular to tangent, and if you want to swap it around, it's fine. But it's not line from the center of the circle. It's not theorem 1. Technically, if you say line from the center of the circle perpendicular to the tangent, you're not wrong. But I'd like you to know that that line is a radius then. It doesn't stop somewhere. So number 8 is your party head.
Oh my gosh.
Okay, this guy has had a lot of party. He's even laying down.
Lord.
What does it say? 2 tangents from a point. What's the complete wording? 2 tangents from a point outside of a circle drawn to the circle in length will be exactly the same length to where it touches and the same length to where it touches. Very often has to do something with congruency. Are you with me? Because that will also be a radius perpendicular using that one. but the party hat is there. Be careful that you don't think let me do it this way. Whatever. Is that a party hat? Because this hat is going into the child's skull. Okay, just be careful that you look at that. Theorem number 9, the most popular one. When I see the tangents are there, I'm immediately inclined to think that the theorem 9 is going to be there. What does theorem 9 say? Just you write tan chord theorem. But what does it say? If ever you have a tangent and you have a chord going from that point of touch has to happen, then the angle between the tangent and the chord will be equal to an angle in the opposite circle segment, because I'm currently in this circle segment over here. So the opposite circle segment would mean you take your fingers and it goes right across to the other side, the circumference. So any which way, that will be then A. Then also indicating that this should then be equal to that one. It's also angle between the tangent and a chord. There's the chord, take your fingers, go to the other side. But you can't stop here in the middle somewhere and have something like that and then think those two are equal to each other. It has to be at the circumference of the circle. Alright, so those are your 9 theorems. What are the other things that you had to do in grade 11? Prove that something is a
Theorem.
cyclic quad, or any of the others as well. We'll go through them now. But the main thing is to prove a cyclic quad. If I just gave you something like that, and I asked you if A, B, C, D was a cyclic quad, what would be the reason? Converse exterior angle of a cyclic quad. Because there are 3 reasons. Converse of exterior angle of a cyclic quad. And the second one would be converse opposite interior angles of a cyclic quad. And what's the third one? Yes.
Okay.
Converse of the bow tie. If you know that they are equal to each other, looks like a butterfly, then that would mean that A, B, C, D is also a cyclic quad, or A and B and C and D are concyclic points. Why is that so? Because it's the converse of angles in the same circle segment. Is there converses of other things as well? Because that's to prove a cyclic quad. Those are the 3 things. Is there converses of other things? Especially number 9, they like it. Somewhere in a question, we've got a triangle and an angle. I don't know what's going on here, but that happens. What can you prove? You can prove, for instance, that line, let's call it DF. DF will be a tangent to circle ABC. The most important thing was that you have to have a triangle. And then you've got A being there, and the angle over there, it's an angle between the tangent and the chord going to the other side, so you were always searching for a little triangle. Seeing the converse of the tan chord theorem. Converse of the tan chord theorem. Even if there's somewhere, and this happens a lot in analytical geometry, if you saw somewhere that on your wherever analytical geometry that this was 90, what could you deduct geometry wise? That AB is the circle's diameter. So if you could get the distance of AB, you could deduct the radius is. And it hasn't happened such a lot, but it's going to happen this year in analytical because you're working with circles. But all of the converses are still there. So that's in a nutshell, basically, just revision of what happened in grade 11. Happy?
Okay.
So right into theorem number 1. So people like calling it 11 theorems. I like calling it grade 11 ones is 9 theorems, and in grade 12 there's 2. But that's 11 theorems, basically. In actual fact, we have 3 theorems in grade 12, but the one is about Pythagoras that you've known forever, that we're just going to look at again in a little bit of a different way. But the main thing for grade 12 is there's 2 of them. The general theme of them, it's all about ratio and proportion. Ratio and proportion. What does that mean? What is a ratio? Something like a fraction? Something like 1 over 2 or 1 to 2 or 50 to 50? Right? 50-50 would be 1 to 1. Alright, so that's a ratio, and a ratio can always be written as a fraction as well. Similarity we're not going to look at today. That's theorem 2. Similarity of triangles. So we're going to be working a lot with triangles. Right. So in the triangle that I've started drawing here, I want to show you what theorem 1 says. And theorem 1 says the following. If there's a line drawn parallel to one of the sides of a triangle, then the sides will be in proportion. What does proportion mean? Proportion means the same ratios. So, for instance, half and 2/4, that is a proportion. The ratios are the same. So you're going to just learn the terminology. So we're going to look at proportionally. What is happening is that that proportion of the sides to each other will be equal to each other. So we've got something like, if this was 10 and 5, and this was 20, what do you think this would be? Oh, you're so clever, because that's proportion. They will be divided in the same proportion. Now, let's just not look at numbers yet, because that's the nice easy ones, and that can happen in November in a matric exam. It can happen. That your proportions will be the same. So I'm saying that the theorem says, if there's a line parallel to one side of a triangle, line parallel to one side of a triangle, it'll do the following. It will divide the other 2 sides. Make sense? So it's parallel to one side, so it'll divide the other 2 sides. Proportionally, or in the same proportion, or in equal ratios. That's what proportion means. It's in the same proportion. Luckily, you know we have abbreviations, so the nice thing here would be, the abbreviation is just line parallel to one side of a triangle. Much better. One line parallel to one side will do what? Will cut the others in the same proportion. But this should remind you of something grade 10. In grade 10 you did. Who can still remember? The
midpoint theorem.
And it's got everything to do with this, but this is just a very specific scenario of this theorem. Because there is parallel lines, and what did it do? If you had parallel lines, there was a little addition to it. You had to know that it cut these 2 in half. Half. What did it do to this side then? Also. And this could have been 5, 5, and 7, 7. Doesn't matter the lengths. But if there was one side parallel and one of the sides were bisected, the third side would also be bisected. And even more than that, if this was like 5 centimeters, this would have been, can you still remember that? DE was always half of BC, or BC BC was twice DE. That was the midpoint theorem. Is that still true? Is it still this thing that says a line parallel to one side will take the other two and divide it in the same proportion? Exactly. The proportion is just 1 to 1 and 1 to 1. It's the same thing, but very specific because it was 1 to 1. And in that 5, 10, 1 to 2 scenario, it doesn't happen here. Because this is a very particular one, the midpoint theorem. Do you remember the midpoint theorem? The other way that the midpoint theorem was asked was also if I gave you, and it could be any which way, right? If I gave you the sides were equal to each other, what could you deduct? Then these lines would be parallel. And still, one is half of the other one, or one is double the other one. So that doesn't fall away, it's still there. When you can use it, you're allowed to use it. But the midpoint theorem is just a very specific scenario of this theorem that says, only thing I need is the parallel lines. The moment there's parallel lines, I know that there's a ratio that's the same. But it's not going to be 1 to 1 and 1 to 1. It's going to be something like 5 to 10 and 20 to whatever, I can't remember what I wrote, 10 to 5 and 20 to 10. Has to be the same ratio. Same ratio means that they are in proportion to each other. Happy on that? So the new theorem, that sketch that was here, please just go add to that. You've got the theorem that says that a line parallel to one side of a triangle will divide the other two sides in proportion. Meaning what? You're going to deduct that AD over DB would be the same as AD over DB would be the same as AE over. You got it. It's a lot like the grade 9 stuff that you used to do 3 years ago. But the reason for that now is the new theorem. Namely, of a triangle. That's it. But it can be taught in many, or asked or required in many ways. I could have said dB over AD is the same as, follow me, dB over AD will be CEEC, doesn't matter? Happy on that? For the same reason. Or AB over AD, AB over AD, AC AE. And I like to talk about the whole thing over the top one. The whole thing over the top one. It could be the bottom one over the top, bottom over the top. The bottom over the whole thing, the bottom over the whole. Are you following here? It's just the same. It's easy. Let's have a look at an example. If I ask you to find x here, guys, this was grade 9 work. This was grade 9 work. We needed ratios and proportions. How do I find x? Very important, you wouldn't be able to find it if I didn't tell you that the lines were parallel, because that's the essence of it. And actually, it's a good thing to always write DE is parallel to BC before you even start, knowing that you can use the theorem that says line parallel to one side. So to find that x, what would you say? Do you need to say dB over AD, etc., etc.? You don't have to. You can, it's good. I don't like it, it's too much writing. Just jump into the sum and say it's x over 15 would be the same as 10 over? That's it, guys. You don't have to say EC over AE and BB over DA. And the reason for this is parallel to one side of a triangle will do what? Will divide the other two sides in the same proportion. Same ratios equal to each other. And then solve for x. Boom, finished. Please give me an answer. And it doesn't have to be a whole number.
50 over 30.
50 over
Correct.
And that's it. And you can write it as a decimal, you can write it as a mixed number, it doesn't matter. Okay, happy on that? Right, let's have a look at a homework sum. I think you must just do number 3 on exercise 10.1 for me.